Okay, so good afternoon, morning, or good evening. Kung ano mang oras ninyo pinanood yung video na to. So this video is will be a walkthrough of the uh, module number 5 on EEE 158, which focuses on analog to digital conversion. So ayun, fortunately after a while, naka-release din kami ng module. And this is actually primarily meant to be done in the simulator. So actually, kung gagamitin niyo siya for the actual pick, for the actual DevBoard, may mga additional na kailangan idagdag na lines and kailangan palitan na lines doon sa sample code. So, ayun, ang focus ng week na to is on analog to digital conversion. So, if nag-take din kayo ng EEE 153, ito rin yung actually topic nyo for this week. So, analog to digital conversion or ADC. Well, ang analog to digital converter, or tinatawag na ADC, is a device that is used to convert a voltage or sometimes current into a digital code or set of bits. So, meron tayong different types of ADCs na kino-consider for our discussion. So, either unipolar or bipolar, which means na positive lang yung input natin or positive and negative pag bipolar, and then either voltage or current yung input natin. So, as with any electronic component, yung voltage units natin are specified no ating electrical ratings and must be respected to prevent damage to the component. Ayan. Some signals yung can't exceed yung ating ADC supply voltage. So, kailangan natin ng processing in order to protect our circuitry. So, and then yun, ADCs built into microcontrollers are usually unipolar and voltage type. So, ayun, ang conversion from analog to digital is just like a mapping operation. So, for example, ito yung kung yung input natin is the x-axis and yung digital output natin is over here, and we have 4 bits. So with 4 bits, we have 0 to 15 digital codes. So yung 000 hanggang 1111. So yun yung 4 bits natin. Put that down. So 0000 hanggang 1111. So every step dito represents one digital code. So for example, ito 5. Yung digital level na to is 0, 1, 0, 1, which is equivalent to 5. And yun, so for this range of input values, ang ating digital output ay 5. And basically, kukunin lang natin yung ratio between yung Vin tsaka yung reference voltage ng ADC and multiply natin with the total number of steps. So parang minap mo lang siya talaga. So papansin nyo dito, pag dumami yung bits ng ating ADC, dumadami yung steps. And then pag lumalaki yung, so basically yung Vin over Vref, yun yung ratio ng analog side. Tapos you can say na yung digital code natin, pag divide mo by 2n, equal siya. So parang, so kung si digital out, divide mo kay 2 to the n, approximately makukuha mo yung Vin over Vref. So parang na-preserve lang yung ratio ng ating Vin over Vref doon sa output over 2 to the n, and 2 to the n siya yung number of steps natin doon sa ating ADC, sa possible outputs. So, ayun. And ito, may several variations. Ito, greatest integer function. Yung iba, this integer function or ceiling, ito is floor yata siya. And meron din namang rounding off and rounding up, rounding down, rounding off. So, depende siya doon sa particular ADC na ginagamit natin. So, for in this case, ang ating ADC ay kinukuha yung floor. Then, ayun. So, makikita nyo dito, kita mo yung mga steps. So, 16 steps lang naman. So, you can see yung difference between each step. Pero pag pumunta tayo, for example, to a 10-bit na ADC, yung mga steps natin are a little more granular or mas maliliit. So, pagka kinuha natin yung response niya, it doesn't look like a step function. No? So, mas malapit na sa ideal. Pero pag zoom in mo to, of course, pag zoom in mo siya at a particular part mo, kung pa rin yung same nature na ito. So, what you can see there is if we have a higher resolution, mas malapit sa ideal yung makukuha nating result. Okay, so that was a bit more of a background on ADCs in general. So we can move on to the next part, which is yung specific na ADC sa PIC32. So the PIC32MM has a 12-bit analog to digital converter, and then it can operate in 10 or 12 bits and conversion speeds of up to 200 kilosamples per second in 12-bit mode, 300 kilosamples per second for 10-bit mode. So here we can sacrifice a little bit of speed to get a bit more accuracy, and then or it can be a bit faster but be less accurate. So meron tayong up to 17 analog inputs, internal and external. And ang ating reference voltage. So the one we compare the input signal to can be internal pins, yung Vref plus, Vref minus, or actually, ito pala yung external pins, Vref plus, Vref minus, and AVDD at saka AVSS siya yung default na power and ground na ating PIC32. Then, meron siyang automatic scan and compare different channels. So, channel scan yung tawag. And then, it can have different trigger sources. So, pwede mag-convert to timers or to an external pin or some other events, or pwede rin naman manually sineset yung conversion. And then yung ating conversion result, actually may different types of encoding. And then configurable din yung interrupt generation ng ating ADC, and can be operated during CPU sleep and idle modes. So actually, pwede natin tingnan yung block diagram over here. So yung input to our ADC. So meron tayong differential operational amplifier over here. And yung negative end niya is always connected to AVSS. Pero yung positive, it can be connected from A and 0. So analog input 0 hanggang AVDD. So kung titignan niyo yung mga pin diagrams natin, for example here, check nyo si pin, for example, RA1 or si RA0. Makikita nyo over here na meron silang AN something number. So ito yung analog input number nila. So not every pin can operate as an analog pin. So for example, CRB, kung na-experience nyo before, CRB7, I think, and CRB7 ay RP11 lang, pero CRB13, CRB13, ito si RB13 is also AN8. So, pagka kino-configure natin yung push button kay RB7, kahit wala tayong galawin sa analog select register, okay lang kasi walang analog pin na connected sa kanya. Pero pag si RB13, kailangan natin specify na yung analog select natin sa kanya is 0 to ensure na digital pin. Mag-function siya as a digital pin kasi siya yung connected to a analog input. So, ayun, as with any other peripheral, kung ano mga timers ng CCP module, we have special function registers to configure yung ating ADC. So, meron siyang total of 4 na control registers. So, control 1, 2, 3, and 5. Galing, walang control register 4. Pero ang ginagawa kasi ng microchip, if meron mga, kung sa PIC32MX, siya yung meron control register 4, and then wala siyang control register 5, for example, kasi medyo yung functions per control register, medyo nire-retain yan across different families. So for the PIC32MM, yung kanyang ADC, hindi relevant sa kanya yung functions ng control register 4, so wala siya ng control register 4. And then meron tayong CHS, so this is channel select, kaya CHS. And then CSS yung channel scan, na hindi naman natin kailangan pansinin since hindi natin siya gagamitin for our purposes. And then meron yung compare hit register na hindi rin natin gagamitin for our exercise today. Pero when you explore on your own time. So, medyo marami-rami yun naman ng control registers. So, 4 nga sila. But the most used ones are actually compiled in this module. So, one of the first important ones is yung ating on bit to turn on and turn off the ADC. And then, meron tayong another bit to set kung 10 bits ba or 12 bits yung ating device. So recall na if we want it to be more precise, yung ating yung ating conversion speed is 200 kilosamples per second pag 12-bit mode and 300 kilosamples per second pag 10-bit mode. So whichever yung mas important kung accuracy ba or conversion speed. And then yung digital result natin has several formats ng kanyang pagka-save. So ito yung buong listahan. So either signed fractional, integer. So maraming iba't ibang options. Although for our purposes, ang pinakagagamitin natin is yung integer na 16-bit kasi siya yung pinakamalapit sa normal na integer for programming in C. So integer na 16-bit. And hindi naman nag-matter sa atin yung signed or unsigned kasi yung ating reference voltages naman ay medyo fixed naman sila. And we're pretty sure na positive lang yung may input natin kasi part of the electrical characteristics ng ating device ay ang pins natin kaya lang nilang i-contain ng voltage is from negative 0.3 volts to 4 or 6 volts. So madalang lang tayo makaka-encounter ng negative input na voltage. Kaya yeah, most probably ang gagamitin natin is yung 16-bit na integer or probably 32-bit na integer din. Then next we have ang next option natin is to automatically sample and convert the signal. So using to be able to automatically sample and convert, you need to make use of interrupt handling, and for the interest of time, medyo hindi na natin siya i-tackle for this course. So pwede nyo siyang gawin in your own time. And so yun, to minimize complexity, we resort to manual sampling by controlling the SAMP bit and ASAM to be 0. So since we are doing manual sampling, SSRC, so sampling source, needs to be 0 as well. So SSRC, siya yung conversion trigger source. We're using yung 0, which means yung manual na conversion. So dito makikita niyo yung different ways to trigger a conversion ng ating ADC. Then, ayan, VCFG, siya yung magko-configure ng ating reference source. So we can either use yung internal na AVDD and AVSS or yung external na VREF pins natin. So kung babalikan natin sa pin diagrams, merong VREF plus and VREF minus pins supposedly over there. Yeah, actually hindi sila mahanap, pero they're supposed to be there. And then moving on. So yung channel scan, enable naman natin CSCNA. It's just set to 0 yung time of channel scan. So what channel scan does is, since isa lang yung ADC ng ating microcontroller, for several different analog inputs, parang mag-jump siya between them. So, puntahan natin yun. So, ito sa reference. So, for example, mag-check nyo muna si AN0, and then si AN1, si AN2, si AN3. Masastore sila sa ADC buff 0, 1, and 2. And then, and so that is basically yung channel scan na tinatawag natin. Since isa lang yung ADC, yung ating microcontroller, ginagamit natin yung same ADC to basically read yung input natin across several pins. But again, for the sake of simplicity, and para agad tayo matapos, hindi na natin siya formally ipo-cover in this course. So, ano pa ba yung relevant? So, yung mga covered pa dito sa ating lab exercise is yung pag-PD ng ating channel. So, okay, sa reference manual. So, ang next nating titingnan actually si code 5, actually what I'm gagawin dyan. And then, so CHS, channel select. So si Chon A, unfortunately, isa lang yung pwede dito. But for other PIC32, sa MX actually, pwede mong piliin yung several, I think AN0 to AN6 to be negative input. And then, for the positive input, yun yung mas relevant for us. For example, dito sa sample code yata dito, ang ginamit is si AN3. And then, sa ating microcontroller naman, actually, yung, sure kung makapakita ko, RB3, yung ating potentiometer over here. RB3 or AN11. So, something to take note of for later. So after nun, yun nga, if we want to use AN3 as our input, we need to configure AN3 to be a input pin, na an analog input pin. And then yung ating result, masostore siya to ADC buff, ADC1 buff 0. So makikita naman natin dito sa block diagram na ating ADC, masostore sa ating ADC buffers ang output ng ating SAR ADC. So in manual sampling mode, ang nagmamatter lang naman sa atin is yung first buffer. But for example, if mag-automatic sampling ka, you can set kung magkakaroon ng interrupt every n or every 4 conversions. So masostore or mababasa mo from ADC buff 0 hanggang ADC buff 4 yung ating output pagka gano'n. And then I think one thing not covered here is yung sa ADC Con3, which is yung ADC conversion clock select. So our ADC requires a clock signal as well, and it will be using a scaled version ng ating peripheral bus clock. Either yung peripheral bus clock, which is yung system clock din natin, or an internal RC oscillator. So yung RC oscillator ni ADC is, I think, nasa 32 kHz, if I'm not mistaken. But hindi ko pa, yun yung sa ano kasi, PIC32MM MX. So sa PIC32MM actually hindi ako sure. But in any case, ayun, since ang requirement niya dito for let's say yun sa 12-bit mode or sige 10-bit mode, 10 bits. And since SAR ADC tayo, if familiar kayo how it works, it needs at least 1 cycle per bit. And then kung yung maximum natin is so ayan, meron tayong 10 bits. I mean 10 cycles for conversion. And then meron tayong maximum na 300 kilosamples per second. So yung conversion, kaya natin sabihin per sample. Meron tayong 3,000 kilohertz or 3,000 kilocycles or 3 megahertz na sampling time maximum. So if yung peripheral bus clock natin is 4 megahertz, so yung required natin na ang ating ADC conversion clock natin, we must set it to be at least 2 para maging kung 4 megahertz yung peripheral bus clock, PD clock, if i-times 2 natin yung kanyang period, that will be making 2 megahertz para mag-work ng maayos yung ating ADC to operate within yung operating limits niya. So, and so merong sample code in the appendix of this module, and I have it loaded here sa MPLab. So itong main.c. So let me just set it as yung aking file to execute. And then let's try it first with the simulator kasi dun siya originally intended. Okay. So yung ating code I guess mas specific lang siya. Kung ano man yung sinabi dito, yun in-explain dito, yun lang din sila here. So ito yung ating enable or ADC on. ito yung ating form, yung mode, ASAM, SS source, yung ating reference, configuration, yung channel scan mode, and then yung ating negative input and ating positive input. So, and then ito ang ginamit natin for this example, si AN3, yung ating input, which corresponds to RB1. So si TRISB1, ginawa natin siyang 1 to be an input, and si ANSB1, ginawa rin natin 1 to be an analog input. So once everything is set, tsaka lang natin isa-set na 1 si sample to initiate yung sampling. Then, kailangan lang natin hintayin yung ADC to say na it's done by reading yung done flag. So for this example, we are just polling it. But yun nga, if naka-automatic sampling tayo, this can be done with an interrupt. So, ayun, pagka-poll na ating done bit, we can just read yung ADC value sa ADC1 buff 0 and store natin to our own variable, the ADC value. I-set natin to 0 si done, and i-set natin to 1 ulit si sample to start sampling again. Now, once si sampling, we just wait for 5 cycles before we set sampling to 0 to start the conversion. So, lagyan lang natin dito, each sampling. So parang each conversion natin is 2 parts. So sampling. So each reading has 2 steps, yung sampling and conversion. So conversion or quantization, yung gamit ko na term for yung 153 na materials. So quantization. So medyo same lang naman yun. And so pag si sampling equal to 1, dito siya sa sampling. Pag nag-sampling equals 0, dito siya sa baba. And then to know na tapos na, magiging done equals. So to start yung conversion, we set samp equals 0. And to know na tapos na yung conversion, we read that done equals 1. So, ayan. So yung process is na-set na 1 si samp. Maghihintay ng 5 cycles. Since we need yung sampling time natin is at least 5. Actually, at least 3 lang ata. But in this case, we have 5. And then we have 5 cycles. And then we have yung sample, yung samp bit, gagawin natin 0 to start yung conversion. And then once it's 0, we wait for the ADC done bit to be 1 to wait for the quantization. So, yun naman siya dito. So, in order to see this in action, lipat ko lang yung breakpoint dito pag nagpasa na talaga. Simulator, right? I think I need to restart yung aking empty lab. I think our simulator is ready. So let me just start to run it. And then, let's just, unfortunately, we can only use yung ating watches and to monitor yung ADC output. Kasi yung logic analyzer natin, wala siyang kakaya ng show ng multiple bits, I think. So, okay, so the program is running and the program has stopped. So Let me just add yung ating logic analyzer. Time na. So, naka-set dito sa akin si AN3 to monitor yung kanyang output. So, once we step into, yun, so naka-default naman na 0 lang si AN3. So, pwede natin gamitin yung logic analyzer. Pwede natin gamitin itong analog input with our stimulus. So, stimulus over here. And actually, tinitingnan nyo sa watch, ang ADC value natin is 0 kasi 0 volts lang naman yung output. So we can set AN3, can set it to a voltage. So in millivolts, let's say, I think may nakalagay dito sa, excuse me, sa ating module. Set natin to 1,400 millivolts. And let's fire it. So, ayan, ang ating input is from 0 volts here, nasa 1.4 millivolts. And then, i-play lang natin yung ating code. So, si ADC value naman natin ngayon is nasa store C, 6E4. So, when you convert that to decimal, that's so that is 1,764, which is approximately 1.4 over 3.3. Yung 1764 over 4096. So once we fire a value na nasa gitna ng 3.3 volts na source natin, let's say that would be 3.3 over 2, 1,650 millivolts. Let's fire that. So makikita natin tumas na konti yung ating voltage, and let's just let it on hanggang sa next na sample niya. And ayun, so we have 81F na input, which is, pag pinag-convert natin, 81F to decimal. So that is 2079. So 81F is 2079. Tapos pagkakunin natin, 2079 over 4096. It's approximately 0.0508. So hindi siya ganun ka-exact na kalahati, but it's around that area. Kasi 1.65 is around half ni 3.3 volts. So meron tayong konting offset. So recall lang yun sa ating figure kanina. Because of this greatest integer function or yung floor function, medyo mas mahirap for us to get it exactly there at the middle. Kahit na kalahati ng reference voltage ng ating input. So that is using the simulator. Now we can also use yung actual na ating device. So gamitin na natin yung ating video over here. Kanina pa nandyan. So actually, madaya ako. Gumamit ako ng LCD screen here just so that I can output yung ating ADC reading. Since there's no actual way to read it unless mag-debug tayo. So, ayun, ang ginawa ko lang dito. So, the changes I've added. So, first is, dun sa appendix na code is wala yung ADCS na line. So, I added this line. since yun nga, ang calculation kanina, 3 megahertz yung sample clock na kailangan, ay 3 megahertz yung clock na kailangan mo ADC natin, so 3 megahertz or lower. And since 4 megahertz yung ating peripheral bus clock or system clock, we need to set na times 2 no system period yung clock period ng ADC converter natin. And then dito naman yung input natin is AM11. So if we look at, if meron kayong schematic ng ating DevBoard, you'll see na yung ating potentiometer is connected to RB3 or AM11. So dito sa channel select natin, 11 yung nakalagay kasi analog channel 11 siya. And then yung configuration naman dito, input si RB3. So, channel 3. And then si ASB is nakaset to 1 dapat yan. Okay. Ito na. Hindi yata pinto. And then, ayun, enable lang yung ADC and then initiate sampling. So, ang ginagawa ko lang dito is yung ADC value ko is naka-display as yun, AN11. And then yung equivalent niya in volts is yun, 3.3 volts times yung ADC value over 4096. So, let me just reconfigure to upload it to the board. And so pindutin lang natin yung upload. So yun na naman yung changes. And may additional code lang ako dito for the LCD. So if gusto niyo ng sarili yung LCD display, meron akong pinost na link beforehand. And ayun, I can share you the code if you need it. So actually, yung uploaded naman na is yung code na to. Ito may LCD. So, ayan. You're seeing na yung ating output is nasa, ang ADC output natin is nasa 3,000. If I turn the knob, so iikot ko lang yung potentiometer to the left para lumiit yung resistance at liliit yung voltage output niya. So, recall kanina, if yung ating input ay nasa 1.4, ay, hindi ko actually na-record. Pero let's say nasa 1.65 volts. At so nasa 2,000 something yung ADC value niya for 1.65 volts. Kaya if hindi kayo naniniwala sa akin na tama yung output, actually have a multimeter over here to verify. So meron lang akong nilagay na resistor para madaling So hindi naman talaga connected yun. Kailangan ko lang ng metal wire para masuksukan ng probe dun sa ating input. And hopefully gumana pa. Hindi mapala siya. So, ayan, ang ating reading is nasa 1.62 volts din through a multimeter. And yung equivalent natin ng voltage according doon sa ating conversion is nasa 1.63, 1.62 volts. So, ayun, it's working. Right. So, ayan, nakuha natin yung ADC value here. Then, ayan, pag pinihit natin sagad to the left, may 0. And then pag sagad to the right, may 3.3 volts. And so 4096, since naka 12-bit mode tayo, if for example gawin natin 0, si mode 12, so 10 bits yung ating input, kailangan natin palitan ng konting ating equation. Instead of 1496, this will be 1024. And i-upload natin, what you'll notice here is yung analog natin dito, umabot ng 1496 ngayon. Later, magiging 1024 na lang yan. But yung equivalent voltage natin should remain the same at around 3.3 volts. So now, yung output ng ating ADC is hanggang 1024 na lang. And if I rotate yung ating potentiometer, ayun. So, iba yung nakuha natin na digital code since iba yung resolution natin. But if we adjust yung ating formula to get the voltage, it will still get around the same voltage. Pero yun nga, magkaiba ng resolution, magkaiba ng precision and accuracy. So, yun actually ayan, yun yung actually yung from the appendix na source code with some konting edits. So, si ADCS ginawa kong 2. So, by default, this will be, I think, 1. And then si channel select A natin is 11. And then si TRISB3 yung inaan natin. So, changes for actual. So, ayan, you can accomplish naman yung ating module using the actual board or through simulations. And if you're not using the actual board, hindi naman necessary yung dalawang lines na po. Iba. So, and that's actually the end of the ungraded part ng module. So you have questions over here na I think you need to answer. Lalagay nyo as, I think, a text file or a comment on the code. I think nakalagay naman dito sa instructions earlier on. And then sa graded part naman, so siguro I can show you how they should work. So for this first exercise, yung sweet spot, so depende doon sa pihit natin kung yung input voltage natin ay between 0.8, 0.1.6, and 0.2.4. May iba't ibang states yung ating LEDs. So, ayun, it's this code. So, I'm gonna be careful not to show the code. So it's uploading. Slowly. And I think it's uploaded. So yan. So initially, patay yung mga LEDs. If my input voltage is between 1.6 and 2.4, yeah, so nasa between 1.6 and 2.4 na ako. Pag pinindot ko si RB7, sisindi yung dalawang LED. And then, pag maging greater than 2.4, pinindot ko si RB7. So, inikot ko si potentiometer, but nothing changes. So, ayun. Walang magbabago pag pinihit ko si potentiometer. So, magbabago lang yung states pag pinindot ko si RB7. So, pagka nasa 0.8 to 1.6, yan. So, pag pinindot ko si RB7, iba na states. So, RC7. So, pag less than 0.8 volts, so parehong patay. Then, yung dimmer naman, basically, i-retain mo yung functionality dito sa earlier exercise. But this time, if pindutin mo si RB13, magsiscale yung brightness ng ating LED. So initially, yung brightness ng LED is around 50%. If isagad ko yung input voltage, magma-maximum voltage yung mga LEDs. So hopefully napansin nyo siya. It looks a bit brighter. And ayun, if nandito ako sa mababang voltage ng input, pag pinindot ko si RB13, magdidim sila. But they're still on. So pag pinindot ko naman si RB7, nandun pa rin yung functionality. Ibang so basically, pressing RB7 determines kung alin LEDs ang on, and pressing RB13 determines yung brightness ng LEDs. Then the challenge is actually very similar. Yung RB13, instead of 2 LEDs, we are controlling using RB7 and RB13 yung ating color combination na ginamit in the previous exercise or previous challenge actually. So let me just set this as my project and load it. So depending on the potentiometer value, pag pinindot mo si RB7, baliktad pala. So medyo baliktad yung ginawa kong code. RB7 pala yung brightness, RB13 pala yung sequence. So yung ginawa ko sa akin, RB7 yung sequence and RB13 yung brightness para similar siya sa nauna. But anyway, how it should work will look something like this. Okay, so connection failed pala. And then, so sinushow ko lang dito sa screen na to yung current na value ng analog reading natin. And then ito yung state, ito yung mode, ito yung brightness natin, 0.5, yung default. So mode ko is nilagay ko na 3 kasi at the start ng operation, dito sa gitnang mode, freeze at current position. So if ang aking potentiometer is nasa 0 to 20%, and pindutin ko si so in my case RB7, but yung actual dapat 13. So pressing RB7 causes yung color change na states from 1 to 3, 4. And then if nasa 20% ako, that's around 800. Yan. Pag pindutin ko siya, so now it's changing every 0.4 seconds. Now it will be changing every 0.8 seconds. So medyo mas mabagal siya magpalit. And then, baliktad din ako. Normal order to, so from 0, 1, 2, 3, 4. Pero pagka dito ako sa extreme, other extreme, naka-reverse order 4, 3, 2, 1. So meron several things na baliktad sa ginawa ko. But yung gist of it is ganyan. Now, pag pinindot ko naman si RB13, siya yung magkocontrol ng brightness. So ngayon, magma-max brightness siya. So hindi ko maximum brightness siya kanina. And then, pipihit ko na lang dito sa other side. to make it a little dim. Pagkapindot ko kay RB13, and yung brightness natin nasa 0.2 lang. So, less liwanag. So, ayun. So, hopefully, kahit medyo may binaligtad ako, magets nyo pa rin yung gustong mangyari namin dito sa inyong challenge. So, for submission, ayan yung mga questions doon sa dito. Please find them with the bold text. You add them as a text file, yung inyong sagot. And then, 3 zip files, yung isasubmit nyo. So, and 1 zip file for each, for the 2 exercises and for the challenge. Submitted via Ovlet. Tentative deadline is December 17, but on bala doon. Okay, so that will be all for this walkthrough video. If you have any questions, just let me know. Siguro yung, if you have your own LCD, I can share you yung aking code dun sa pag-generate ng output niya. And some standard functions. Anyway, that will be it for me here. Thank you very much for watching, and see you around.